Hi, Mathman here. Today we're going to take a look at something that is really not one of my favorite aspects of mathematics, but it's crucial, and it's usually a branch of mathematics that is introduced to a student before they learn calculus. And this branch of mathematics is called linear algebra or matrix math. And basically, a matrix is an arrangement of numbers in an orderly way and performing operations on these numbers such that there's scalar multiplication, there is matrix multiplication, and so on. And it allows mathematicians uh, an easier way, and that's why it's done, because nothing is done in math to make things harder. They always look to doing things in a way that will make it easier for the mathematician to solve, let's say, a series of problems and so on. I'll give you an example, and I think that probably this is the best example because it's usually the way linear algebra is introduced. It's useful in terms of um, what solving systems of equations and finding the common intersection points between different linear equations. And also, it's good at representing vectors because of the way the operations are performed. It's very much like vector multiplication. And it's used especially in computing because computers can perform these orderly operations on large matrices, whereas doing it by hand, it would take forever to solve these things. But matrix math is ideally suited for performing certain computations on computers. And in a spreadsheet, you can create um, matrices and solve them. You can find the transpose and other things that uh, are particular characteristics of matrix algebra, matrix math that you'll be performing. So, why don't we get right down to it? So, like I said, a matrix is an orderly arrangement of numbers. So, we we have a we usually put it in a large bracket, and then we say this is position A11, A12, A13, and A21, A22, A23, and that's a 2 by 3 matrix. We got 2 rows and 3 columns. Um, Another matrix would be something like this: A11, A12, A21, A22, A31, and A32. And you can have different arrangements of numbers. In these, you can have uh, square matrix, square matrices, or square matrix, where, well, let's see if we carried this bracket down further. This would be a 3 by 3 square matrix. A 3 1, A 3 2, A 3 3, and you could see that these sub indices that they denote the position of the number in the array. They call this an array also. This is a matrix array. So A11 sub 11 denotes this position. A22 denotes that position, and A sub 33. And it's all for keeping things in order when you perform operations. Now, why? Well, I think it's always good to understand why matrix math can be useful in solving a complex system of, let's say, linear algebra. So let's say we have an x, we have a formula y equals 2x minus 3, and another where that's y, 2y equals 1x plus 4. Okay, and that would be, we could, what we want, now we know these are lines, okay, so let's imagine our x, y coordinate system, and when x is 0 on the first, we'll call this 1 and 2, equation 2. When x is 0, y is minus 3, so we have 1, 2, 3, and that's where it crosses the y-axis, and we have the x-axis, and then the y is 0 when x is 3 halves. So when x is 3 halves, y is 0. So we got 1, 2, 3, 4. This is 3 halves is right there, right at this point. It's 1.5. And so we have another point there. Remember, in order to draw a line, you always have to have at least 2 points to connect. All right, let's say x is 3. So x is 3. So we got 6 minus 3 is 3. So we go up 1, 2, 3. 1, 2, 3, 3. So we have a line that goes like this. Okay? And that's our y equals 2x minus 3. Well, we know these aren't parallel because in order for lines to be parallel, they need to have the same slope. And the slope is different between these two equations. In fact, there are many more equations that are not parallel than there are that are really parallel that you'll encounter. Although I assume there are probably an infinite number of equations that can be parallel, and an infinite number of equations that would not be parallel. So I don't know. I guess it doesn't doesn't really matter. But let's put it this way. In many cases, you're going to run into equations where the lines are not parallel. In this case, we'll divide through by 2. So we have 1/2, and this would be 2. And so when x is 0, y is 2. 1, 2. So x is 0 and y is 2. And when x equals -4, y equals -2 plus 2, so 0. So 1, 2, 3, 4. Y is 0 over there. And you can already see that when I connect these lines, they're going to cross at some point right there. So you can see these lines are not parallel, and they're going to intersect at some point. So let's say y is 4. We got 4, 1, 2, 3, or x is 4, 1, 2, 3, 4. Y would be 6, 1, 2, 3, 4, 5, 6. Of course, this is hardly precise in any sense of the word. 1, 2, 4, 6, up there. 4. No, I'm so sorry, 4. If x is 4, that's 2. 2 plus 2 is 4. So 1, 2, 3, 4. And 1. So our point is right there. It's near the point of intersection. Now you can see that we have these two lines and they're not parallel. Well, what is this intersection? Where at what value x do these two lines intersect? Or, in other words, have the same value? Where are they located in space? Because this is a representation of space, two-dimensional space. And where in space do these two lines meet? That's the question. So we could go about it in an algebraic way. And usually that's not too hard, but it takes a little bit of doing. First off, you got to get the equations in such a way that they are easier to work with. Okay, I was interrupted with a phone call, so it kind of threw me back a little bit, but this is where we were. And I was giving you an example of showing how to solve for a system of equations where two lines meet at some point in space on the xy coordinate system. And what we need to do, and doing this and showing you that matrix math is a way of simplifying how to do these calculations. So what you would do algebraically here is write this equation in such a way that it's easier to work with. So here we would manipulate this equation by subtracting y and adding 3. Okay, so we'd end up with an equation 2x minus y equals 3. That's the same as the top one. And down here we would have x on 2 minus y equals minus 2. Now, these are the same equations as the ones above, but now we can work with them in such a way that we can eliminate one of the variables. And we do that, we can, right off the bat, you can see you can eliminate the y variable by multiplying one of the two equations by -1, and then adding the two equations. So if we did that, we would have minus 2x plus y equals minus 3. And you can see that doesn't change the equation any. It looks different, but it doesn't really change it because we multiplied all the way through with -1. And down here we're left with x on 2 minus y equals minus 2. Okay, so if we add these two equations together, you got minus 2x plus x over 2 plus y minus y equals minus 3 minus 2. All right, so the y's cancel, and this is the same as minus 4 halves. So minus 4 halves plus 1/2 x, okay, that's 3 halves x, equals minus 5. Okay, so we have minus 3 halves x equals minus 5. So minus 3 halves x equals minus 5. So as we see here, we have minus 3 halves x equals minus 5. So now if we multiply both sides by minus 2/3, we have minus 2/3 and minus 2/3. We have that cancels, and we have x equals minus 10, or minus 5 times minus 2 is 10, 10/3. So x equals 10/3. Now we can take a look at the other variable. We want to solve for the y variable. And we have to eliminate the x's. And how would we do that? Well, if we multiplied by minus 4, the bottom equation by minus 4, so let's multiply this bottom equation by minus 4. We end up with 2x, I'm writing the top equation, equals 3, and that's minus 2x minus plus 4y equals 8. And now we add these together, and we got 2x minus 2x, that cancels. We got minus y plus 4y. Whoops. A little ahead of myself there. Plus 4y equals 11. These cancel, and we got 3y equals 11, or y equals 11/3. So y equals 11/3. So that's our point in space where those two equations intersect. Okay, now this is all well and good. But what happens now if we throw in something like this? We have 2x plus y minus c equals 0, and that's a three-dimensional. Okay, three-dimensional z, x, y, and it makes some sort of plane when Z is 0, Y is 0, 2x can take any value there. And you create some, I'm just some plane in space, in three-dimensional space. And we can have different planes intersecting in three-dimensional space. And something like that, where three different planes intersect. And so you want to find those values at which they intersect. So you have 2x, let's say we have x minus 2y plus z equals 3, and 4x minus y plus 2z equals 1. Okay, how do you solve that? It's very, 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 very cumbersome because you have to now find ways of eliminating two variables, and when you add all three, to isolate one. So that becomes much more difficult a problem to solve than, let's say, 2x plus y equals 1 and x minus 3y equals 2. That is a far cry from linear algebra of this sort. So this is where matrix math comes in handy. And so what you would do is you can solve a problem like this by drawing a matrix where the 2, 1, all the coefficients of the variables. So these are the x coefficients. The y coefficients go into this column. 1, minus 2, minus 1. And these are the z coefficients. This is minus 1, 1, and 2. And so now you have this matrix that represents those three equations. And what you would do now is you would perform a number of operations in order to allow you to find the solution to these equations. The first thing you find is something they call the determinant, and it's represented by this delta. And that's called the determinant, which is a denominator to all of the, well, it'll end up being a denominator in the end when we see how we perform the operations. So now we have this matrix, okay, and we've got to find the determinant of this matrix. So there's an easy way. What we do is we have a formula for that, and I'll write the formula down in a minute. But first off, we eliminate all of the, we eliminate these and we find what we call the minors. We find the minors of the determinant. And in this particular determinant, there is an easier way to find the minors, but I'm going to just show you this so that you can see that we can use this form of matrix math to solve this complicated system of equations. So we have 2. We write this 2, 1, 4, 1, negative 2, minus 1, minus 1, 1, 2. And then we rewrite the first two columns again. 2, 1, 4, 1, minus 2, minus 1. Now this only works for 3 by 3s, matrices. Okay, this trick only works for those. Now we multiply these diagonals, and when we go from left to right in the downward way, they're positive. And when we go from the bottom to the top, left to right, they're negative. So we have, all right, let's know if you can necessarily see this. Right, try to angle the camera a little better. Okay, so we have these three down in this diagonal. So we have 2 times minus 2 times 2 plus 1 times 1 times 4, and plus we have minus 1 times 1 times minus 1. Now we go to the negatives. Minus, and we're going to just leave it like that. We have 4 times minus 2 times minus 1 plus minus 1 times 1 times 2, okay, plus 2 times 1 times 1. Okay, so now once we get all of that done, let's find a little space on this board. Okay, we'll keep our main equations and we'll just erase this matrix here. And our determinant, we're going to write like this. Determinant, or equals that, equals, okay. 2 times 2 times 2 is 8, but we got a negative in there, so that's minus 8. We got 1 times 4 plus 4. Negative 1 times negative 1 is 1 times 1, so we got positive 1. Now we have minus, okay, minus 2 minus 1 times minus 4, so that's 8. And we have minus 1. And we have, what did I write there? We have, I'm sorry. Okay, that's minus 4. Let's see. Minus, okay, we have minus 4, 2, 1, 1, 1, 1. Okay, minus 1, 2, 1. So that's minus 2. All right. Yep. And we have 2, 1, 1. So plus 2. And again, that's minus, so we have equals minus 8 plus 4 plus 1 minus 8 plus 2 minus 2. These cancel. This is minus 16, 20, okay, minus 16 plus 5. So that's minus 11. Minus 11. All right, so our determinant is minus 11. That's our determinant. So we're going to write that up here. We'll keep that in storage, minus 11. Okay, now we rewrite our, boy, I hope I got my math right. You can see how complicated this would be if we tried to eliminate variables. Boy, that could get really messy. But just writing matrices, now What we do is if we want to solve the X matrix, we rewrite the matrix again. We got 2, 1, 4, 1, minus 2, minus 1, minus 1, 1, and 2. But now we want to solve for the X variable. So in this column, which represents the X variable, we put in 0, 3, 1. And then we write 0, 3, 1, 1, minus 2, minus 1. You can see how this becomes cumbersome. So now to solve for the X variable, we take this operation that we did before and then divide that by the determinant, and then we have X. All right, so that's what we're doing. That's where we're heading. So in order for us to do this, again, now this again only applies to 3 by 3 matrices. Don't try this with other matrices. Okay, so, and I'll show you why later. I'll show you the exact formula later. I just want to show you, just for the ease of calculation, how a matrix allows you to solve this system of equations. So here we have 0, 0 times negative 2 times 2 plus, okay, we got 1 times 1 times 1 plus minus 1 times 3 times minus 1 minus, again, these diagonals are all negative, so we put minus bracket, so we have 1 times minus 2 times minus 1. These, and then this diagonal plus minus 1 times 1 times 0, and then this one plus 2 times 3 times 1. Okay, so we got 0 plus 1 plus 3 minus, okay, now we're going to, it's important to keep this done orderly. You can really mess up your plus and minus signs if you don't keep track. So minus, okay, minus 2 times minus 1 is 2 times 1 is 2. This is 0 plus 6. But remember, this is all negative, so we got 4, and this is x equals x without the determinant. Okay, this is the determinant times x. All right. So, well, let's not do that right now. X. All right. So we got 4 minus 2 minus 6. All right. So we got minus 8, and 4 is equal to minus 4. So x is equal to minus 4 on minus 11. So x equals 4 elevenths. See, we got the x right off the bat using this. So x equals 4 elevenths. All right, so, and we don't want to lose our determinant. Our determinant is minus 11. All right, now we want the y variable. Yes, this is labor intensive, but it's a lot easier than trying to find ways of eliminating variables. So we rewrite our matrix to 1, 4. This is our original matrix. Now we're looking for the y variable. So we replace the y's with the 0, 3, 1. 0, 3, 1. And we rewrite these first two columns, 2, 1, 4. Again, this is a trick only applicable to 3 by 3 matrices. So we go diagonally this way, which is positive. So that's 2 times 2 times 3. So that's 2, 3 times 2. And again, we're solving for y right now. Okay, 0, 0. That's times 1 times 4. We know that's 0. Plus negative 1 times 1 times 1 minus, now the upward diagonals, times 4 times 3 times negative 1 and plus 1 times 1 times 2 plus, and that's 0. Okay, so we got 4 times 3 is 12 plus 0 plus minus 1 minus, and that's minus 1 there. So we got plus 12 and we have minus 2. Okay, so, and that's 0. So we have equals, it's not exactly y, let's call them y prime. We have 24 minus 3 equals 21. So y equals 21 11ths. And that's a negative because we got a minus 11. So, y, again, y is equal to that 21 divided by the determinant, which is minus 11. So now we got 2 points. We could either substitute them into one of these equations and find the z, or we can just continue with our operations and find our z value. We'll call this z prime. Z prime. All right, so again, we redraw the original matrix. We got 1 minus 2 minus 1. Now we're solving for the z, so we got to substitute in for the z column the 0, the 3, and the 1. And then we rewrite our first two columns. And 1 minus 2 minus 1. Again, positive, these diagonals. Okay, so that's 2 times negative 2 times 1. So we got 2 times negative 2 times 1. We got plus 1 times 3 times 4. And this one's 0. Plus 0 minus, all right, this is 0. We got minus 1 times 3 times 2 plus 1, 1, 1. 1 times 1 times 1. Okay, so here we got minus 4 plus, that's 12, plus 0 minus 0. Minus minus is plus 6 minus 1. Z prime equals. All right. And z equals z prime on the determinant, and our determinant is minus 11. All right, so let's get these all in order here. So we have 18 minus 5, and that's equal to 13. Okay, so z equals 13 on minus 11. And now we got all three answers. You see how matrix math made the solution of a very complicated system of equations simple for us to solve. And if we plug these back into the original equation, we'll find that these will yield the answer we want. So here, 2x, so x is 4, 11, plus y is minus 21, 11, minus z, which is minus 13, 11, is equal to, so we have, whoops, I'm sorry, almost lost my glasses. We got 8 elevenths plus 13 elevenths minus 21 elevenths equals 21 elevenths minus 21 elevenths equals 0, and we got the answer. And we can do that for the other two. And in this case, we'll end up with 3. In this case, we'll end up with 1. So we found our answers using linear algebra. Okay, so I gave you that demonstration first to show you the utility of matrix operations, because a system like this one I'm now erasing from the board is very difficult to solve otherwise. Okay, so this has really been a piece together type presentation. So we saw the utility of matrix math. Now we're going to take a look at some of the characteristics of matrix math. We're going to be talking more in generalities. So, for example, we have square matrices, which are like A11. And now this just tells the position, the sub 1, A12. So the 1 represents the row and the 2 represents the column. We got A13, and we got A21, A22, A23, A31, A32, A33, and typically you're not going to get problems more than a 4 by 4. A 4 by 4 matrix, you're gonna really have that there's a lot of computation involved with that. That's why this is ideal for computers. And you can see how something like this could also represent vectors, because remember how we had vectors that we got I plus bj plus ck, and that would be some vector A. And we could have another vector b equals bi plus bj plus ck, and or b, I'm sorry, b, oh, I don't know, what am I doing here? You got to get a d, e, and f. Okay, so and how we add and subtract, very much like what we're going to see with matrix math. Now, if we have a matrix A, and we're going to call this top one A, and we have a matrix B, we have, let's say B is 1, 1, B 1, 2, B 1, 3, B 2, 1, B 2, 2, B 2, 3, and B 3, 1, B 3, 2, B 3, 3. What if we want to add A plus B? Well, like vectors, we add like components. So this is going to be a little large. We got A 1, 1 plus B 1, 1. Second position, A 1, 2 plus B 1, 2. And A 1, 3 plus B 1, 3. And we have that all the way through. 2, 2 plus B 2, 2. A 2, 3 plus B 2, 3. And last, we have A 3, 1 plus B 3, 1. A 3, 2 plus B 3, 2. And A 3, 3 plus B 3, 3. So like vectors, we add like components. So like a vector, AI plus AJ and A, darn it, BJ, CK, and B is equal to B or DI plus C or EJ plus FK. All right, so we got A plus B equals, well, we got A plus D, I plus B plus EJ plus C plus FK. So we have to add like components. That's similar to matrix math. And that's why in some cases vectors are represented by matrices. Now, the next thing we want to do is multiply matrices. So that's a little bit more complicated. We take the first row and we multiply that by the first column to get the first position. So we go 1, 2, 3 for the first three positions across. So A times B, and this is going to be a little bit harder to represent on this board, but we got A 1, 1, B 1, 1 plus, okay, A 1, 2, A 1, 2 times B 2, 1 plus A 1, 3, A 1, 3 times B, this is a 3, 1, B 3, 1. That is our first position. Now you can see our second position is this row times that column. So that's A 1, 1, B 1, 2 plus A 1, 2 times B 2, 2 plus A 1, 3, B 3, 2. And our last position all the way over here, it's going to be a little challenging to write the room. So we got that multiplied by that. So that's A 1, 1, B 1 3 plus A 2 1 B 2 3 and plus A 1 3 times B 3 3. Now we got to do our second row. So we've done that. Now we got to take this and multiply each column by the second row of A's. So we got A 2 1 B 1 1 plus A 2 2 B 2 1 plus A 2 3 times B 3 1. Now we take that and multiply the second column. So we got A 2 1 B 1 2 plus A 2 2 B 2 2 plus A 2 3 times B 3 2. And the last position for the second row is A 2 1 B 1 3 plus A 2 2 B 2 3 and plus A 2 3 B 3 3 or 3. Let's see, what did I do? Okay, A 2 1 B 1 1 A 2 2 B 2 1 A 2 3 B 3 1 A 2 1 B 1 2 A 2 2 B 2 2 A 2 3 B 3 2 A 2 1 B 1 3, okay, A 2 2 B 2 3 and A 2 3 B 3 B3 A 2 1 B. Okay, I'm going to this last column B3 3. And finally, this last row multiplied by the last column gives us our last positions for this multiplied math or multiplied matrix. So we got A 2 1 B 3 1 or 1 3 plus A 3 2. What am I doing? I'm sorry. I got to do the first column. Ooh, you see how easy this gets to mess up? A 3 1 B 1 1 plus A 3 2 B 2 1 plus A 3 3 B 3 1. That's the first position. A 3 1 B 1 2 plus A 3 2 B 2 2 plus A 3 3 B 3 2. And lastly, A 3 1 B 1 3 plus A 3 2 B 2 3 and lastly A 3 3 B 3 3. So that and that. All right, and that's your resulting multiplication. That's when you multiply two vectors. together. And remember, it's this column or that row by each column gives you the positions of the first row. The second row multiplied against the three different columns gives you the three positions for the second row. And lastly, the last or third row gives you the positions of the bottom or third row on the bottom. And it's quite calculative intensive to do these sorts of things. So that is how you multiply two matrices. There's another type of multiplication they call scalar multiplication, which is if we had a matrix A and we wanted to multiply that by z times A. So we would say ZA equals Z times this matrix. And that's basically just this factor multiplied by each individual matrix component.
One matrix, two matrices.
Matrices is two, yes, one matrix and two matrices.
You just said two matrices.
I'm sorry. I got it screwed up. Sometimes it's a little hard to keep the language when your mind's trying to think at the same time. So that's my problem. I don't walk and chew gum very well. All right, so when you have the scalar multiplication, z times a, each position of the matrix is multiplied by z. So ZA11, ZA12, ZA13, ZA21, ZA22, ZA23, and finally ZA31, ZA32, and ZA33. And that's like very similar to matrix multiplication in vectors. So we have three. We looked at three different. Ways of dealing with matrices, and we'll look at these in a little bit more detail. Again, matrix math is not the easiest. Linear algebra is not the easiest topic to master. There's a lot more that we can do. I think it's a matter of practice. Quite frankly, you don't use matrix math unless you have many systems of equations or that you need to solve, or something that's going to be very computationally full of computational labor, where you're going to use a computer or a spreadsheet or something that's going to aid you. The matrix format allows you to be able to do these operations in an orderly way over and over again, and it can be computed by a computer much more quickly. That's why it's suited for that type of thing. It's not really suited for hand calculations very well. That's why very rarely do you ever see anywhere in college anything more than a 5 by 5 matrix. That right there would involve, let's say, finding the determinant for such a matrix would be involve many calculations. But we're going to look next time. We looked at scalar already, scalar multiplication. We looked at, which is z times a. We looked at matrix multiplication, where you got a matrix A times matrix B. Next time we're going to look at a transpose And we're going to look at the meaning of a transpose matrix. And we're going to look at different types of matrices and their characteristics, like a 2 by 3 matrix. And if you have, for example, a 2 by 3 multiplied by a 3 by 2, I think you end up with I'm going to have to check this, but again, I think you end up with a 2 by 3. And so, but matrices become transformed into other types of matrices if you perform operations on them. So we're going to look at all these different characteristics. I'm just giving you an example here. I could be wrong, so please don't take that as hard and fast what I just erased. But you can, through multiplication, take a matrix that you start with, a 3 by 2, and end up with a 2 by 3 matrix. So we're going to look at all these different things. We're going to look at determinants and the actual formula for determinant. We looked at a special case for determinants for 3 by 3 only. And that was a special case that makes it simple for us to calculate this diagonal multiplication. Um, what we're going to be looking at for larger matrices is what they call minors, and that's how we're going to calculate a determinant using minors. And so we'll go into those aspects. This is a very intensive aspect of mathematics. You won't really run into it too terribly much unless you're, let's say, a computer scientist in a scientific field. Then you're going to deal with very large matrices, and you're going to need supercomputers to calculate the results for these matrices. So a matrix is just basically a way of organizing numbers and performing operations in a logical manner that gives you the results that you desire. Like I said, given that a system of 3 by 3 equations, it was much easier to solve them using matrix than trying to eliminate the individual variables. That's why I gave you that example first, so you can see and get a feel for the utility of matrix math before actually learning the different operations and calculations of matrix math. So this is Mathman. Hoping that this wasn't too bad for you. Again, it's not my favorite form of mathematics, and, but it is essential to learn or to be exposed to, at least to some degree, before we enter into calculus. So this is Mathman wishing you well until the next video.